Welcome back for part two. So this part is going to mirror very similar to the last part one of this video, except this time we're going to apply with letters or variables, which are just basically representing unknown quantities. So if when I see like an A and I'm like, oh boy, I'm not really sure what to do, I just might call it something that I just don't know an amount of, like 6 times the amount of apples I have, or 6 times, 2 times the amount of bananas I have. But the actual truth is when you start using sort of letters and variables, in some sense, it's a little bit easier because instead of actually solving it out and adding and multiplying it, you can just leave it as 6a or 6 times a. So often that kind of people sometimes get a little bit stuck on it, but really sometimes it can be easier. For this example, we're looking at a similar thing, like I said, except with variables. So we have 6 times a plus 2b. And in this case, we're multiplying those two. We're going to once again talk about this distributive property and how it can help us create equivalent expressions, which are your sort of two learning targets for this kind of module that you guys are doing. So we're going to look at the same kinds of structures we did in the last example, but just look at it with letters. So I'm going to first, and once again, just to remind you guys, you should be thinking about which one of these boxes makes the most sense to you and what can you explain in the discussion of this module that can kind of really help other people who might be struggling with that one. So you might just think about that. Which one of these lettered boxes do you feel like you're going to kind of speak to? So if we look at this sort of first example, I'm going to think about it as like the area of a rectangle. I'm taking 6 and I'm multiplying it by a plus 2b. Now like we did in the previous video, you've got to find kind of the areas of doing the length times width of each of these boxes. However, notice that here, instead of doing like 6 times 2 to get 12, I have 6 times a. Well, guess what? 6 times a, that's just going to be 6a. And I've got 6 times 2b. Let me make that 6 a little better here. 6 times 2b, which, well, 6 times 2 is 12, so that's just going to be 12b. And I can actually leave it just like that. I don't have to simplify it. I don't have to change it at all. I could just write 6a plus 12b. And that is the expression that's equivalent to this expression using that area model. And notice I'm going to kind of, like I did in the last video, go right down here to the distributive model. A lot of times people think of it like this. I'm taking 6 and I'm multiplying it by a, and then I'm doing 6 and I'm multiplying it by 2b. But really, it's that idea that you're trying to find the area of a rectangle that's made up of those two different sides of that rectangle. But regardless, I end up with the same expression, 6a plus 12b. Now, some of you might be thinking a lot about this learning target of how you can represent different expressions. Some of you might have represented this as 6a plus 6 times 2b. Notice that I did not multiply the 6 times 2 together. I mean, even though we can say 6 times 2 is 12, but this expression is a different expression, but equivalent to this one, which is equivalent to that one. So if I'm going like I did in the last example, I've got right here 4 different equivalent expressions. My original expression, I've got this expression, which you can see in the area model or the distributive model. So I'm just going to check it here. And I've got this expression. Right now I've got three equivalent expressions so far that I can use to all represent the same basic expression. And you might be able to figure out how to make another one that's equivalent out of this, and we're going to be looking more of that in a minute. But I'm going to slide over here because this multiple groups model is going to be a very, very important model when you're thinking about this with variables. Similar to what I did in the last example, I want 6 groups of a plus 2b. Remember, multiplication means an equal amount of groups. So I really want 6 groups of a plus 2b. And I can think of that like with the area model or the distributive model like we did in box A or box C. But I'm going to think of this multiplication as repeated addition. Just like you did in the last example, if I think of that as my group of a plus 2b, and I need 6 of them, then what I'm really creating is a really, really long expression of 6 of these that are all being added together. I've got 6, I've got a plus 2b plus a plus 2b plus a plus 2b plus a plus 2b, And you can see it's a little bit like longer and it's kind of a little bit of a pain. But this whole thing is an equivalent expression that is also equivalent to 6 times a plus 2b, because I've got 6 equal groups of a plus 2b all added together using repeated addition, which is the same as multiplication. Now, the reason that this could be kind of a nice model to think about is that when you're combining some of these things, you don't always have to just combine all of the a's together. For example, if I kind of combined this a, and this a, and I got 3a, and then I did this 2b, that 2b, and that 2b, and got 6b, and then did the same thing with the other side, this a plus this a plus this a, but instead of making that 3a plus 3a, which is 6a, because I have that here, I'm just going to write it as 3a. And I'm going to write another 3a plus another 6b. This expression, even though it is not simplified, which means it's not like just 1 terms for the a's and 1 terms for the b's, or 1 apples and 1 banana, I still have an expression that is equivalent to it. If I think of this as 3a plus 6b plus 3a plus 6b, in the end, I will have a total of 6 a's and 12 b's, which is equivalent to not only this, but it's also equivalent to that. So this allows you to be able to create all sorts of different kinds of equivalent expressions. For example, I could maybe take 4 a's. And if I was thinking about where I'm going, where I need 6, then I would need to add 2 more. And then I could take, I don't know, let's say 10 b's. And if I'm thinking about where I'm going, I need to get to 12b, so I would need to add 2 more. And that one still ends up with 6 a's and 12 b's. Notice that as long as I am getting the same amount of each kind of term of the expression, each letter of the expression, then I'm going to get an expression that's equivalent, and that allows me to create all sorts of different kinds of equivalent expressions. And this is something that when you get to the Padlet in this module, that's something I want you to kind of explore as a group, to kind of make a bunch of different equivalent expressions based on one starting expression. And then also in the last example, we talked about this idea of factoring. So if I start with 6a plus 12b, and I think of, instead of multiplying, I'm going to think of dividing it out. I can think to myself, well, what number goes into 6a, 6, and 12? And what if it does, then I can pull it out and write an equivalent expression. For example, I can see right now that 2 goes into 6 and 12 goes into 6. So I'm going to pull a 2 out. I got a 2, and then I have to think about, okay, 2 times what will get me to 6a? In this case, it would be 3a. And then I'm going to do the same thing with the b's. 2 times what gets me to 12b? Well, that would be 6b. That expression is also equivalent, and that's that idea of factoring out. I'm going to kind of try to draw this the way I did before. Thinking about pulling out something that is in common from both of these terms, and then writing it in a form that you might have used the distributive property for, like we did in the beginning. So I can actually do that with a couple of different things. If I'm thinking about another number that goes into 6 and 12, you might have seen that 3 goes into 6 and 12. So if I'm thinking about it with 3, I've got 3 times what gets me to 6a? Well, that's going to be 2a, because 3 times 2 is 6. And then 3 times what gets me to 12b? Well, that's going to be 4b, because 3 times 4 is 12. Now notice I can use that idea of factoring to create 2 other additional expressions. So all in this kind of model, I've got here 1, 2, 3, 4, 5, 6, 7, 8 expressions that are all equivalent to my original expression, 6 times the quantity a plus 2b. This idea is really important because it's not only talking about this idea of how the distributive property could be seen in a lot of different ways, but also that all of these can be used to create equivalent expressions, which is really the kind of heart of that second learning target that we've been talking about in this module. So there is a little bit of some practice that we're going to do. I'm going to kind of look at these, and you can feel free to pause the video and jot some of them down on a piece of paper in front of you before we kind of solve them together, so that you have an opportunity to think about it. I wouldn't just kind of watch it, because sometimes you need to kind of have a chance to practice it. But this first example is, I just want you to use the distributive property to write an equivalent expression. So I've got 3 times quantity z plus C. If I was to use that distributive property, what would I end up with? And that's the same thing with all 5 of these expressions. So you might pause the video and then kind of work a little bit and then replay it and see how many you can get correctly. I'm going to kind of pause for a second and then I'm going to solve all 5. All right, so let's solve this one here. If I'm thinking about this as 3 times z, now notice that does represent 1z. It doesn't have a 1 there because the 1 is kind of implied. Like you wouldn't say, sometimes you say I have a banana, not that I have 1 banana. So often we kind of shortchange that, and that is the same in math here. That means 1z, or 3 times z, which is going to be 3z, and then 3 times c, which is 3c. So I'd have the expression 3z plus 3c. Now, once again, I could do what I did up here and build this out into something that is completely different, but also equivalent. Like I could do z plus z plus z plus c plus c plus c. That would be something that is equivalent to, I could do z plus c plus z plus c plus z plus c. There are lots of ways to create an equivalent expression besides using the distributive property. So you can keep that in mind as we're kind of working through this. Similar, I've got 10 times 4, which I know is 40. And then 10 times 8, which I know is 80. And I end up with 120 because 40 plus 80 is 120. Now, some of you might have kind of saw, like we did in the last video, 8 plus 4 is 12. So 12 times 10 also is 120. So you can see that there are lots of kind of ways of thinking about this, especially when you don't have variables. But when you have variables, it gets a little bit more kind of consistent. Here with the distributive property, 2 times 6c is 12c. And now notice here I've got still 2, I've got a minus 3 here, but I'm still going to do 2 times 3, which is 6. The only thing that's going to change is that instead of putting a plus sign in between, I'm going to put a minus sign. But everything else is the same. 12c minus 6. Now what I'll say is, some of you might say, oh, well, 12 minus 6, that's just 6c. But notice, these are not the same thing. I have 12 carrots here, and I'm taking away $6. I can't take dollars away from carrots. They don't combine, or they don't subtract. So we just leave them separate. You just leave 12c minus 6. And then similarly here, notice that here's multiplication. I can distribute this way, though. There's no reason that I can't. It still means the same thing. I have 5b minus 32, and I want 4 groups of it. So in this case, I've got 20b, and I've got, let's see, 32 times 4. I'm going to quickly do this here. 128 is what I got here. And so I've got an expression 20b minus 128. Similarly, and I don't know if I'm going to have a ton of time to do this, but you might think about how to do this kind of work that we did in box D, but this idea of pulling out or using division. So for some of you that need a little bit of a challenge, these are great kind of challenge problems here for you to think about. And I would pause the video right now and think about them. But this is the idea of doing the opposite. What number goes into both of these, and then how can I pull it out? What number goes into both of these, and how can I pull it out? So pause the video, give a chance to think about it, and then see if you can solve it with me. Okay, in the last kind of minute here I have of this screencast, I can see right away that 5 goes into both of them. So if I think of this as 5 times what gives me 40? That's going to be 8. 5 times 8 is 40. And then I'm going to do 5 times what is 25? Well, that would be 5. Now notice, if I wanted to check my work, I could do 8 minus 5, which is 3, and 3 times 5, which is 15. And if I did 40 minus 25, they both end up giving you 15. That's why they are equivalent. So that's something that you can do when you don't have variables, when you just have numbers. You can use that idea of evaluation and using order of operations to solve. And then similar here, I can also see 5b and 25d. I've got 5 as my common factor. So I'm going to kind of pull it out, and I get 5 times 1 in this case. Excuse me, 1, and this would be 1b. Now you could just write b. You don't have to write 1b, but I'm going to put 1b there just because I feel like I'm not sure if, because I got 5 times 1b would give me 5b. And then 5 times 5d would give me 25d. So I could actually write this expression as 5 times the quantity b plus 5d. So I once again want you to kind of go back to thinking about which letter in this box makes the most sense to you. This idea of using the area model, multiple groups model, the distributive model, or the factor model. And I want you to go into this discussion and be able to choose a model and explain why did it make the most sense to you. All right, thanks.